Dr. Smith leads the Nutritional Biochemistry Laboratory at the NASA Johnson Space Center. This group is charged with keeping crews healthy with respect to nutrition, including research to understand how nutrition can mitigate the negative effects of spaceflight. Dr. Smith, I give the floor to you.
Well, again, as mentioned, my name is Scott Smith, and I lead what we call the Nutritional Biochemistry Lab here at NASA. I hope to try to give you a bit of an overview today of the type of work we do, what the backdrop is, and why we do what we do, and then give you some feel for some of the research that we've done recently and where we might be going in the future. So I'm a nutritionist. I got my Ph.D. in nutrition, and I am a very biased nutritionist. So I will be quick to tell you that every system in your body that you care about depends upon nutrition. And I list many of the systems here in white, again, to make that point, that your diet and nutrition affect all of these things. And when we talk about spaceflight, the things that I have shown here in red are the elements of spaceflight, or some of the elements of spaceflight, that impinge upon nutrition. So things like changes in gravity environments, the food system, the amount of water available, the atmosphere, the radiation exposure, all of those things can affect not only these physiological systems, but can also affect nutrition. And we need to understand the interrelationship of those things to make sure that we're keeping the crew as healthy as we can. Now, we worry about performance. Acutely or in the short term, the things in yellow that are shown here, these can change relatively quickly. We know that diet can affect hydration status, which can affect a lot of things. We know it can affect cardiovascular function, inflammation, kidney stone risk, all the way up to cognition, the ability to exercise, and behavior and performance, morale, things like that, sleep. All can be affected by your diet or your food intake on relatively short durations. Over longer durations, we tend to worry about diseases. And I show several here in yellow, and these are all diseases that have nutrition components to them. Now, that's not to say that nutrition can cure cancer or prevent you from getting osteoporosis or prevent muscle loss and sarcopenia. But diet, if it can't stop those diseases, a good diet can help mitigate them, and a bad diet will exacerbate them. And when we talk about putting people, again, into space for a very long time, these are the types of things we're worried about. Cancer risk associated with radiation, osteoporosis risk associated with bone loss. And we can use the food system as a way to help protect the crew. And if we don't do that, we will put the crew at greater risk of diseases that might affect the mission, or certainly will affect their long-term health after the mission. Now, my lab does what we call two types of work. We do operational work and we do research. Operationally, we work with the space station crews. We've done that since 2000 when we sent the first crew up. And in large part, we are working from a nutrition perspective to keep the crews as healthy as we can. Before and after flight, we do a detailed biochemical assessment of the crews to make sure we send the crews up in as good a health as possible. That when they come back, we collect blood, we collect urine, and we go off and look at vitamin status and mineral status and kidney stone risk and a number of other factors so that we can work with the flight surgeons so that as they work to get the crew members back to full health after flight, that they use nutrition as a tool to do that. During flight, we track two things. We track body mass, and we do that using the device here in the middle that you can see Karen Nyberg perched on. This is the SLAM-D. Everything in NASA has to have an acronym. This is the Space Linear Acceleration Mass Measuring Device. So what happens is the crew member climbs on. You can see it's about a foot away from the wall. There's a knee bar to hold you on, a belly pad, a chin rest to hold you in position very tightly. You push a button, it pulls you towards the wall with a known force. It measures your acceleration, and using the physics of force equals mass times acceleration, we can calculate the crew member's body mass. So this is a way to determine body mass or weight in weightlessness. And that obviously is one of the more challenging things to do in space. But when you think about it, when you go to the doctor's office, the first thing they do is put you on a scale, because tracking your body mass over time is a very quick, very gross way, if you will, to monitor your general health. If you're losing weight and not trying to, that typically means there's something going wrong metabolically. So the ability to measure body mass in weightlessness is extremely important. So this is one of the things we do with the crew. From a nutrition perspective, we also track dietary intake. We built an iPad app several years ago. We flew it 5 years ago, back in 2016. It was deployed to space station. You can see the login screen here as the iPad floats in the cupola. You can also see it here in Peggy Whitson's hand. And what happens is you would push your picture to log in, which would bring you up to this screen on the left, which would be blank. This was built for use in space flight, so the days across the top are the Julian date, or the numbered day out of the year. You would then choose one of the ways up here to start entering foods. So it's an iPad. You can leave a recording, you can take a picture, you can scan a barcode, you can search. There's a quick button here for just water, but there's a folder here that takes you to this page on the right that shows you an alphabetized list of all the foods that are available on board space station. You can filter down. You can see here it's filtering by meat and fish items and vegetables and sides. You can also filter down by category, by origin of which country produced the food. And if it's something that you know you ate this week that you're looking for, again, you can just click on that and this list will get shorter. You can scroll in this list. You can see this is the middle of the alphabet. You would check these boxes here for the items that you ate. The add to consumption button up at the top here would then become highlighted. And when you clicked it, it would bring you back over here. So you would then see this picture on the left. And you can see several items have been selected. For each item, it shows you the number of calories, the amount of sodium, the amount of fluid. If you swipe, you can then see the amount of protein, the amount of carbohydrate, the amount of fat in each of those food items. At the bottom, it gives you a running total of your calories, your sodium, and your fluid. And the little bar at the bottom here, relative to your requirements, shows you where you are during the day towards meeting your requirements. So for calories here, this individual had a requirement of 2,468 calories. The bar starts off at red, turns to yellow, and eventually will turn green. Same thing with fluid, red to yellow to green. And then sodium is the reverse of that, because we don't want crews to get too much sodium. So sodium starts at green and goes up to red. If you swipe this bottom section, you would come to the screen over here, which shows you your protein, carbohydrate, and fat intake in terms of grams, in terms of percentage of calories, a pie chart of percentage of calories, and then your protein intake in grams per kilogram body weight. And again, we're hoping the crew will get that little black bar over into the green area of consuming between 1.2 and 1.7 grams of protein per kilogram body weight. It's very easy to use, it's very intuitive, and it gives them real-time feedback, and they really do love it. We recently, about a week or two ago, passed 4,000 days of crew use on orbit, and we have data on more than 90% of those days. So the fact that the crew fills it out that often tells you just how much they do like it. And the fact that we have that degree of data where we know literally every single item they eat on almost every day on a 180-day mission allows us to dig in deeper, to go look at things like the intake of different vitamins or intake of different minerals in relationship to their physiological outcomes, so that we can start to piece together the role of nutrition in keeping crews healthy. So that all is operational work. That's work that we do for the flight surgeons. The other element of work that we do is research. We are a soft money research lab. We write proposals, we scratch and claw for funding like every other research lab out there in the world. We do ground-based research and we do flight research. The ground-based research is always predicated on trying to find ways on Earth to simulate aspects of spaceflight. So depending on what we're trying to study, we will try to find a way to mimic that. So we will do chamber studies, and you can see one of these. This is at the Johnson Space Center. We use this chamber. We put 4 people in there for up to 6 weeks at a time. And we were looking at things like stress effects on the crew, sleep deprivation, communications delays. And we did a nutrition study in here where we looked at enhancing the food system, asking the very basic question of, if we feed people better, will their health outcomes be better? And we're working up the results from that right now. And I'll talk a little bit later about a flight study that we're following that up. We do bed rest studies where we will put people to bed for weeks or months on end. And this is a great way to stress the bones and the muscles, the cardiovascular system. And you can study not only the deterioration of muscle and bone when you're not using it for extended periods, and you can also test countermeasures. We've done work in a habitat off the coast of Florida, off the southeast United States, where people lived at the bottom of the ocean for 10 days to 2 weeks. And it provides a hyperbaric atmosphere. So it's normal air, but it's at an increased pressure. So we looked at things like changes in iron status and red blood cell metabolism. We looked at vitamin status and oxidative stress, because the oxidative stress is higher in this environment. And then lastly, for ground research, the other thing that we've done is work in Antarctica. We didn't study the penguins, but we studied the people that lived there during the winter. And what we wanted to study there was vitamin D metabolism and vitamin D supplementation, because our astronauts are at risk for vitamin D deficiency. And part of that is because they don't get any ultraviolet light exposure. They don't get any sunlight exposure. So if you want to simulate that, the best way to do that is to go to Antarctica, where the sun doesn't come up for 6 months. So we did a few studies down there looking at vitamin D supplementation in people wintering over in the Antarctic, and just, and I'll show you some of those data in a moment. So the ground-based data we do are sometimes exotic. They are often challenging studies to do, but they're always easier to do than spaceflight research. You can do more controlled studies, you can study more individuals, you can do more invasive studies on Earth. We always test studies on the ground whenever possible, because sometimes we've done bed rest studies and found that the countermeasure that everybody thought would work didn't. And better to find that out on the ground than getting to flight when you want to do your final validation in a flight model. We've had some tremendous opportunities to do flight research over the lifespan of space station, and nutrition research in many ways boils down to 3 things: tracking dietary intake and collecting blood and collecting urine to look at changes in biochemistry and metabolism. So pictures across the top here, you can see Luca Parmitano, one of the Italian astronauts, collecting a blood sample from Karen Nyberg. Nicole Stott here with a centrifuge spitting down blood samples. You rarely see centrifuges in the wall, but that's one of the nice things about zero gravity. Collecting urine becomes very difficult on orbit for research purposes. There is obviously a toilet in space, but it works like your toilet on Earth, which is after you go to the bathroom, it goes away. If you want to collect a sample to bring home, you have to have a special device. And this is what we call a urine collection device. It's got an adapter on one end. There's a male version that you see here, and there's a female version as well. You void into the bag. Before flight, we put a small amount of a volume marker in the bag. They mix it up. There's a port that you can sort of see there that you would put a syringe into the opening. You'd withdraw a few 7 or 10 cc's of urine. The syringe goes in the freezer. You see Chris Cassidy here loading up the -80 freezer with those samples. And then this urine collection device goes back in the Ziploc that it was supposed to be in and goes in the trash, and typically goes into one of the vehicles that does not come back to Earth. They jettison it from space station and it will burn up coming back through the atmosphere. To show you some of the data we've collected over the years, I mentioned vitamin D. The line here is serum 25-hydroxy vitamin D concentrations. I'll point out that in any of the data I'm going to show you, these are mean plus or minus standard deviation. And these are in crews that were supplemented with 800 international units of vitamin D per day. And that is obviously enough to maintain vitamin D levels at a very good level. The green line here at 80 nanomoles per liter is what many people advocate as being the optimal vitamin D. In the US, at least, the red dotted lines represent the range that is considered normal. And again, 800 international units of vitamin D is enough to maintain people in that window while receiving no sunlight exposure. So it doesn't take a lot of vitamin D to get to optimal levels. The two graphs that are inset here, I'll spare you because I don't think I have time to go into them in detail. But in short, these are the two studies we did in Antarctica. And in one of them, we found a relationship between vitamin D status and stress and viral reactivation. In short, people that had lower vitamin D status, that had greater levels of stress, had a higher incidence of viral shedding, of viral reactivation. Here, the graph you see is Epstein-Barr virus. But we actually looked at these data last year and published a paper back in July in the journal Nutrition, where we looked at our data relating these factors in relationship to what is known or what was known back then a year ago about COVID infections. And we posited that vitamin D status might be one of the factors that differentiates people that have a relatively mild case of COVID infection or people that have a very severe case of COVID infection. And studies have come out since we published that, documenting that fact that people with better vitamin D status tend to do better when they get the virus. Now, that's not to say vitamin D will protect you from getting the virus, but it will help you in fighting it off once you get it. You heard probably a few times today that bone loss during spaceflight is a significant concern. And when we collected our data and went off to first look at the bone biochemistry data and the bone data, we realized that one of the countermeasures, exercise, there were different devices that we had used for exercise over the course of our study. So when we started looking at the data, we had to split the groups into individuals that exercised with what we call the IRED, which you can sort of see on the left. IRED is the interim resistive exercise device. And then in 2008, we launched the ARED, or the advanced resistive exercise device. As the name implies, the ARED was better. It provides for more loading. It provides for more exercises, and just all around was a better piece of exercise equipment. The interim device is the one that we had available that we could fly when we started flying crews in 2000, and it took us the extra years to get the ARED built. When we started looking at the data, this was rather striking in that when we looked at the bone mineral density data from the DEXA, the ARED subjects are shown here in blue. The crews exercising with the IRED are shown in white. And for comparison, we show astronauts that flew on board the Mir space station, the Russian space station that we flew astronauts to back in the 1990s. And on the Mir, there was no resistive exercise available. Okay. So when you look at the IRED crews and you realize that there's no difference in bone loss between those two groups, this tells you pretty obviously that the IRED was not protecting bone. But the ARED, on the other hand, these crew members did not lose bone. The average was slightly above zero. There is a significant standard deviation bar there, so there is some variability, but clearly some people are protecting bone while some people are not. Regardless, I think you'd rather be in this group than this group. The big graph here is whole body bone mineral density. The graph on the left is the spine. The graph at the bottom is the pelvis. If you look at the manuscript where we publish these data, there are 2 or 3 other regions where you see the exact same pattern. That is, the ARED protected bone better than the IRED. One of the key factors as a nutritionist that we always like to point out is that the ARED crews ate better. They had better nutritional status, they didn't lose body weight, and they had better vitamin D status. And I maintain strongly that those elements are key to this response, because we know for a fact that if you don't exercise, that is, or if you don't eat well, if you lose weight, you will lose more bone than you need to. And eating well is one of the first things you can do to protect your bone, along with exercise. So the fact that some individuals, as I mentioned, didn't have the same response to ARED doesn't bother me. My first response to that is, well, did those people lose weight? So these data are striking in that this was the first time in 60 years of flying people in space that we ever saw people come back with the same bone mineral density that they left the Earth with. And we protected them with nothing but diet and exercise. Now, there's still some nuance to this because this is the bone mineral density. And this was done with DEXA. DEXA provides a 2-dimensional image, X-ray, and it is not perhaps the best way to measure bone density. And there are more studies coming out now looking at what we call QCT, which gives a 3-dimensional estimate of bone density. And what we're seeing is that while the density might be being maintained, the architecture is different. And the reason for that becomes apparent when we look at the biochemistry. So these are two graphs of biochemical markers that reflect bone breakdown and bone formation. And we know that bone metabolism is a balance between these two processes. You are always breaking down bone, or what we call resorbing bone, and you're always forming bone. And if those two things are equal, then your bone density doesn't change. What happens during spaceflight is your bone breakdown goes up. We've known this for some time, and the race has always been on to try to find a way to stop bone breakdown. And when you look at this, the bone breakdown in the IRED group shown in white, in the ARED group shown in blue, are literally no different. So the resistive exercise protected bone mineral density, but it didn't do it by slowing down bone breakdown. What it did was it increased bone formation. Okay, I don't have the data on here, but the bone formation rate is higher in the ARED subjects than it is in the IRED. If you look on the mirror where they had no resistive exercise, there was no response in bone formation markers at all. So the IRED is stimulating some bone formation, but not enough to overcome the bone breakdown. So what's happening is bone breakdown is higher, bone formation is higher, and you're remodeling the bone. So the density is not changing, but you're likely breaking it down in one area and building up in another in response to the exercise. And a key question that we still have about bone during spaceflight is whether or not that bone is as strong after flight as it was when you left. Because it may be that you're changing the architecture to where your fracture risk is higher once you return to a gravitational field. Now, I had to bring these data because speaking to a pharmacology conference, these are as close to pharmacology data that I've got. The bone people always want to go to pharmacology when it comes to bone loss. And there's a class of drugs known as bisphosphonates. And what the bisphosphonates do is they block bone breakdown. Okay. They literally poison the osteoclast so that your body cannot break down bone to release calcium. So the two graphs on the left are the same graphs I just showed you a moment ago, except we've now added in the bisphosphonate group here in the tan lines. And I mentioned that bone breakdown goes up in spaceflight. When you give bisphosphonates, this was alendronate, which was given once a week. And what you see is that bone breakdown in the individuals that took the drug actually was lower during flight than compared to the other individuals. Okay, so in other words, the drug worked in flight. That when you take bisphosphonates, which block bone breakdown goes down. No surprise. When you look at bone formation rates, bone formation also went down. Now, this is not an effect of the drug, but this is an effect of your body being pretty smart. Because when you slow bone breakdown, your body knows it's got to slow bone formation. Otherwise, you're going to form bone at a higher rate than it wants to. And in weightlessness, without loading, your body is trying to get rid of skeleton because it knows it doesn't need the same skeleton in weightlessness as it did on Earth. So when you chemically block bone breakdown, your body will slow down the rate of bone formation. Now, when we look at parathyroid hormone, when you look at the IRED group, parathyroid hormone levels went down significantly. Again, I don't have the data on here, but these data look exactly like the mere astronauts that did not have any resistive exercise. And the reason parathyroid hormone goes down, parathyroid hormone, as you know, is responsible for pulling calcium out of bone. When your blood calcium levels go up because of an increase in bone breakdown, you'll suppress parathyroid hormone release. So again, you're losing bone with the IRED, which is releasing calcium, which tells your parathyroid hormone gland not to release parathyroid hormone because you don't need it. The ARED group in blue, you can see an almost identical pattern line as you have with bone formation. And that is because of resistive exercise, which also ramps up over the course of flight, your parathyroid hormone levels will slowly go up later in flight, which not coincidentally is associated with an increase in bone formation markers. When we look at the effect of taking a bisphosphonate, again, the bisphosphonate blocks the ability to get calcium out of bone. And when your body needs calcium, it will increase parathyroid hormone concentrations. And that's what you see happening in every single blood sample that we collected during flight. That is, the body is working to try to overcome the effect of that drug. When we look at the effect on calcium, first of all, urine calcium with the IRED and ARED crew members, pre-flight, urinary calcium is here, it goes up in flight and then starts to taper off. Okay, again, I maintain mimicking the changes that we saw in bone formation markers. Okay. Many people advocated that if we just gave bisphosphonates, not only would it protect bone, but it will reduce kidney stone risk. And kidney stone risk, as you know, is largely dependent upon calcium concentrations in the urine. The data here are a little bit perplexing because the bisphosphonate group had higher urinary calcium concentrations before flight compared to the other groups. During flight, again, the drug kicked in, blocked bone breakdown, urinary calcium went down over the first month. This is flight day 30. but that by the second month of flight, the amount of calcium being excreted by the bisphosphonate group was literally identical to the individuals that did not take bisphosphonate. And that is true for the rest of the flight. So the idea that we ought to be giving bisphosphonates to reduce kidney stone risk doesn't work. Where this becomes concerning is the graph on the right. Serum calcium concentrations, as you know, are maintained at a very tight level to protect the body. That when calcium levels are too low, you end up with hypocalcemia, which can lead to tetany and other issues. And when you look at this, the bisphosphonate group had significantly lower concentrations of blood calcium. And not only that, was very close to the bottom end of normal limits here. This is the mean and standard deviation. When you look at the individual data, you can see we had individuals that were below normal levels for calcium. That is, they were hypocalcemic. And this is a serious concern. And I would advocate that anytime we want to think about giving any drug during flight, we need to be very careful to make sure that while we may be fixing one problem, that we're not creating another. If we were designing a food system that is optimal for bone, it would have these factors in it. We recently finished a study in a chamber at the Johnson Space Center, working with our colleagues in the Space Food System Lab. This is Dr. Grace Douglas's experiment, and we're working those results. But in the meantime, we've started the flight study, and we just had our third astronaut who participated in the study land. That's Victor Glover. You can see his picture in the top right. Victor was the third subject. And what happens with the study is we fly literally special containers for him for the experiment. And it allows him to select from those foods that we worked out with him ahead of time and each of the crew members. And it has more omega-3 sources. It has more fruits and vegetables. And we literally meet with the crew every week to review their dietary intake, to talk to them about their diet and how they're meeting the study goals and what they can do to do a little bit better the following week. So we're very excited about this and very anxious for those results. Shifting gears, about 10 or 12 years ago, it was realized that some astronauts were coming back from spaceflight with changes in their eyes, that they couldn't figure out what this was. They'd never seen this before. There's some nuance to it, and I'm a nutritionist, I'm not an eye specialist, but there were changes in the retina, that is the back of the eye, in some astronauts. And this went from, we didn't know it was a problem, to being one of NASA's major concerns. Everybody rushed to the idea that this was related to fluid shifts or intracranial hypertension, that when you go into spaceflight, the fluid would rush into your head, the pressure in your head would go up, that pressure would push on the optic nerve, that pressure would push on the back of your eye, and that might lead to these problems. What those ideas fail to take into account is that not everybody develops these problems. And I can't say that enough. Because if everybody developed the problem, you could see how it would just be related to weightlessness. Some people think it's carbon dioxide because when you're exposed to high concentrations of carbon dioxide, like the atmosphere on space station, it will increase the blood flow into your head. Same thing, blood flow into your head increases the pressure, but everybody's breathing the same air. We went in to look at our data because we collected a lot of biochemical data to see if there's anything we could do that might be able to help the physicians trying to understand and treat this. One of the things that we were looking at was several metabolites in what we call the one-carbon metabolic pathway. And this is a biochemical pathway that you might be familiar with. This is a very nutrition-rich pathway. It's got a lot of vitamins tied to it. It's called one-carbon metabolism because this is how the body moves single carbon units around. So you interconvert amino acids, you methylate DNA, all through this pathway. At the center of this pathway is homocysteine. And homocysteine is an amino acid metabolite. It's considered to be a cardiovascular risk factor. And again, it's related to folate and B12 and B6. And if you were to go to the doctor and your homocysteine level were high, the first thing they will likely do is give you a folate supplement. The second thing they'll do is start checking out your heart because they'd be concerned about, again, cardiovascular implications of this. When we started looking at our data in relationship to this astronaut eye problem, I can tell you the day, the date, and the hour, my colleague Sarah Zwart came in after looking at the data and sat down and said, there's something going on with one carbon metabolism. And what she meant by that was that she had come across this graph. And the yellow line here is individuals that develop these eye problems. The white line is individuals that did not develop eye problems. And what she found was significantly higher homocysteine concentrations in affected astronauts. And moreover, she found that the affected astronauts had higher concentrations of homocysteine before flight. And I won't show you the data, but a very similar graph appeared for 3 other chemicals in this pathway. So the 4 chemicals that we looked in this pathway were all higher in affected astronauts, all higher before flight. And I apologize for little things like here where the micron is missing from a micromole. I had to convert the talk from my work computer to my personal computer. And ironically today, more than any, the Greek letters all get lost in the font. So I apologize to all of you for that. When we ruled out everything that we could think that was possible, we started to come back to the idea that genetics might be affecting this pathway and that genetics might be associated with changes in this pathway's function and that could somehow be related to development of these eye problems. We did a study looking at 5 SNPs, single nucleotide polymorphisms. Those are shown here. I'm going to focus in on these 2 on the bottom here. Serine hydroxymethyltransferase 1, the SNP is C1420T, and we highlight here in yellow what we consider to be the risk allele, and the MTRR A66G, where the G is the risk allele. MTRR is a vitamin B12 dependent enzyme. And again, I'm going to focus in on those 2. In short, what we found was that B vitamin status in genetics significantly predicted the ophthalmic outcomes that we looked at. We did a very complex analysis. If you go look in the FAST journal where we published it, all of the details are in there. For the sake of presentation, I show you the graph here today, which to me is one of the more impressive pieces of evidence. This is that one SNP I mentioned, MTRR A66G. Again, I don't know how familiar you are with genetics, but depending on what your mother and your father gave you, you either got an A or a G. So the possible genotype for this SNP at base pair 66 within methionine synthase reductase, or MTRR, you either got an AA or an AG or a GG. Each of these symbols now is an astronaut. And what this shows you is that every astronaut with the GG form of this SNP developed these eye problems. And the fact that this cell is empty convinced many people that we were on the right track. Not everybody believes this, because a lot of people still think this is a fluke and that we have an association between homocysteine and eye problems, but we don't have definitive evidence linking those 2 things. There are a lot of people that developed eye problems that did not have that SNP. And that didn't surprise us. We never expected to find one SNP causing this problem. Moreover, what we think is happening is that this pathway, when it doesn't work well, is affected, and the biochemistry that comes from that is what's leading to these problems. We then did a bed rest study where we put people to bed for 60 days. This was a strict head down tilt bed rest. We were also exposing them to carbon dioxide because, as I mentioned, a lot of people felt that carbon dioxide was part of the problem. And indeed, what we found was that some individuals in that bed rest study developed optic disc edema, which is one of the more serious complications of these eye problems, okay? Optic disc edema is measured by the change in total retinal thickness. And we looked at the subjects in that bed rest study and categorized them by having 3 or 4 risk alleles in those 2 SNPs that I mentioned before, or having 0 to 2 risk alleles. And what we found is that individuals that we would maintain were at risk for developing these eye problems indeed had greater thickening of the retina during bed rest and after than did individuals that did not have the genetics. They had some thickening, but it was much less and it was not pathologic. So again, we maintain that the incidence of optic disc edema during bed rest is genetically predisposed. The other measure of the eye is the retinal nerve fiber layer thickness. And what we found here is that based on the subject's genetic profile, individuals had thicker retinal nerve fiber layers before bed rest than did the individuals without those genetics, and that their retinal nerve fiber layers got thicker during bed rest, while the other group didn't change much. One of the striking elements of this, again, I give my colleague Sarah Zwart full credit on this. She found when we were writing this up that there's a clinical population that has the same characteristics that affected astronauts either have or we think they have, because many of these things we've not been able to measure. But we've shown higher homocysteines, a higher incidence of these SNPs. We think they have elevated intracranial pressure, but we don't know. We think they have an elevated incidence of white matter hyperintensities, which are an effect on the MRI of the brain. We think they have thicker retinal nerve fiber layers. And we know, and we measured this, that they have altered androgen response and altered carbohydrate metabolism. The clinical population that has that same set of characteristics is women with polycystic ovary syndrome. And we maintain that women with polycystic ovary syndrome might just be the analog population that we need to study to understand why, if we were to send them to space, hypothetically, they would develop these eye problems. PCOS is the leading cause of infertility in women. It affects between 10 and 20% of all women. One of the intriguing elements is that the frank cases of eye problems have all been in male astronauts. And we would hypothesize that that may be because, first off, we don't fly as many females as we do males. So it may just be that we haven't flown enough female astronauts to find out that their incidence is the same. But I maintain that we exclude women based on the incidence of polycystic ovary syndrome and altered carbohydrate metabolism, and that is more likely leading to them being screened out during selection, and that's why we're seeing this difference. But again, a lot of that is conjecture. We're in the middle of an experiment with our colleagues at the Mayo Clinic up in Minnesota, where they're recruiting women with polycystic ovary syndrome, women with intracranial hypertension, or both. And we're collecting blood to go look at their genetics and their biochemistry to see if indeed we can document that this relationship is true in these patients. And the potential implications of this are profound. And the question that remains is whether or not we can supplement with B vitamins to counteract this response. And we maintain that giving things like folate and B12 and B6 and riboflavin might be able to alter the biochemistry to change the vascular function, to change the structural integrity of the eye and the blood vessels, to mitigate these effects in astronauts, and also to have positive effects in people on Earth. And we're in the middle of trying to get those studies done. I show you here, there's a URL at the bottom. We've got a couple of our books that we've published that are available for free. The one in the middle is literally brand new. We just put that online about a month ago. And it represents what we call our evidence book, which is, this is literally everything we know about space food and space nutrition. We've updated this every couple of years. So the last version was 5 years old. And it took us that long to be able to update it and come up again. So again, we just put that online. The book on the right is a kid's book. I would say it's the same book, it just has better pictures and smaller words. Both of those can be downloaded from that website. I will tell you that the Space Nutrition book was also translated into Italian by the Italian Space Agency. And if you look on ASI's website, you can find it there. So with that, I will leave you with the picture that I started with. This obviously is your beautiful country. My only regret today, besides the fact that my computer shut down, is that I couldn't be there with you. But again, I thank the organizers and PharmaSpace for the opportunity to talk to you today. And I'd be happy to try to answer any questions that you might have. Thank you.